Thank you for having me here. I'll have I'll first share my slides, and then I would like to express my appreciation for giving me this stage to thank Li Liu, the translator of the Book of Why to Chinese, and to be able to address a workshop which is at the heart of the work that I've been engaged with for the past, I would say, 30, 40 years, and the work that I'm continuing to develop. So let me try to share my slide first. Okay. The topic the title that I chose is, no, has two elements. One is the science of cause and effect. The other one is going from the science and the theoretical foundation to areas that I believe will be the focus of our attention, at least my attention, in the future. One is personalized medicine, or in general, personalized decision making. The other one is computerized ethics. So let me start by talking about the science and look at what I'm going to talk about. I'm going to explain why I consider the work about causal reasoning in the past 3, 4 decades to be the development of a new science. Why we need new science to answer causal questions. Then I'm going to talk about the fundamental laws, or the double helix, some people call them, of causal interest. Fundamental laws, I mean, if you know the laws and if you exercise them, then you don't need then all the answers that you ever hoped to be able to answer can be answerable by mathematics, just by the mathematical derivation as a consequence of these two laws. Then I'm going to talk about 7+1 pillars of causal wisdom. This is going to be sort of a survey of the results that was obtained in the past few decades about causal reasoning and what we can do with it in certain subtopics of application. And this will be the tools. Some people call them tools. I call them pillars of wisdom. And I'll show how they impact several applications area. Then I'll go to personalized decision making and elaborate on that. Good. Let's talk with. I have been talking here about science. Let's see what a scientific approach to that problem could be like. Here's my perception of a scientific paradigm. You can compare it to other paradigms to see what a non-scientific paradigm looks like. Um, this is a box here that contains the science, or the whole picture is a science, because it has input and output. You have three inputs here. You have data of various kinds, collected under different methods. And you have a query, and that's the most important, the research question that you're about to answer or to estimate. Most of the time, it requires estimation of some kind. There is in the background the model of reality, the face of reality that we do not see. We see only a partial picture of reality itself. So our perception of reality is another input. So you have here a box with three inputs and one output. Output is the estimation of the query required here at this input. Um, in the box itself, you have a calculus. You have the logic that allows you to go from these three inputs to the output. And we say that, oh, sorry, I have, no, 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 no. I clicked too hard. I'm sorry, I need to go back to previous. Yeah, go to previous, go to previous. Yeah. I have a problem here of raising my, oh, good, good. A problem is said to be solvable if my model, this is my model, permits the calculus to express the query in terms of the available data. And notice that part of the data is the information about how this data was collected, whether it is experimental data, observational, or combination thereof. So now that you have a three input and one output box, our question is, what should the calculus be like? Even before that, we have to give examples of what we mean by causal questions. And here are my typical causal questions. Perhaps you've seen them in my earlier talks. They haven't changed because they represent really the sum total of what we mean by, or the various kind of causal questions that come out that we consensually agree that they constitute a causal question and not just statistics. So here's a typical question: how effective is a given treatment in preventing a disease? No one would claim that this is non-causal because we have the connective here saying preventive, and I'll mark those certain connectives by a yellow color. You'll see that the yellow connectives will be the characteristic which makes a question causal as opposed to non-causal. So here's an example. Was it the new tax break that caused our sales to go up or our marketing campaign? Here is an output has been observed. The sales went up. And the question is to go from outcome into causes. And you even have here the word causes explicitly in the sentence, in the query. So obviously this is a causal question. Here's another question. Was it the healthcare cost? What is the annual healthcare cost attributed to obesity? It was in the news 2, 3 years ago. You read about it in the New York Times. The question was, can we even define the healthcare cost attributed to obesity, or should we go and talk about the soda that people consume? And you see, we have here a question of attribution. We would like to know to what degree obesity is responsible for the increase in healthcare costs. So this is another kind of question involving attribution. Can hiring records prove an employer guilty of sex discrimination? Again, it's a question of attributing blame. And the last example will be taken from a personal decision making. I, as an individual, am about to quit my job. Will I regret it? It's a personal decision, and I have already made up my mind. I'm about to quit my job. So, in a way, I have the output, and I want to know whether I should really revise my decision. Will I regret it? In this, you have both personal decision making and the element of regret and pausing to think whether the thing which I already decided about should be pursued. So I'm taking these five examples as typical causal questions and would like you to focus on the yellow relationship because what unites them, what's common about them is number one that we have no dissent, no disagreement that they are indeed of causal nature. And the second is that they are not articulable in the standard grammar of science. Why? Because the standard grammar of science is wedded to the equality sign. If we have an equation, for instance, the force is equal to a constant times the acceleration, then the acceleration depends to the force divided by that constant. If we the equality sign is a symmetric connective, but you and I understand that in the world there are some directionality to a certain relationship. For instance, if I tell you that y is the deflection of the barometer and x is the atmospheric pressure, then you and I understand that it is the atmospheric pressure which causes the barometer to move and not the other way around. So what we need to do is to build a science for the connective, directional connective, which is very much like assignment in computer science. You have a content to a certain register. The program look at the content of one register and assign another register to obtain the content of the previous one after a certain arithmetic operation, multiplying by A. So we imagine that the science or the nature looks at atmospheric pressure, X, multiplied by a constant, and assign the barometer a value that is equal to the product of the two, and it doesn't go backward. It is not the case that the nature looks at the barometer and assigns a value to the atmospheric pressure. No. You and I understand that there is a directionality here. Some people think you can derive it from the equations of physics. If you look at the flux of momentum, but this is true perhaps in certain physics-based problem, not in terms of social science. It's hard to talk about a flux of momentum that make you persuaded that that you should take a certain that government should take a certain policy as opposed to another. Here you cannot talk about a flux of momentum. Okay, so but we do have directionality. So whatever I'm going to say now is just an attempt to replace arithmetic, which is wedded to the symmetric equality sign, with an asymmetric relationship, which is the assignment. So I'm going to replace science from being wedded to the equality sign and recast it in terms of relationship. All of them are asymmetric and they look like the assignment operation that we are familiar with. Okay, let's see how far we can do. Here is the assignment. This is what I call the two fundamental laws of causal inference. I'm going to talk about it may look hieroglyphic here, but it isn't. By a model, we mean a collection of functions, M. Then the basic building block is going to be a counterfactual term, y sub x, which means the value that a variable y will take on for a given situation called u or unit, Had X been small x, this is a new kind of relationship normally used as a subscript here. So y sub x will mean the value of y had x been equal to small x, had variable capital X equal to small x. That's not the notation for counterfactual. M will be the model. So here is a very simple relationship saying if you want to compute the counterfactual y sub x, it's very easy. All you have to do is find the y, the actual value of the outcome y, but in a different model, in a model which is mutilated. I call it m sub x. How is it mutilated? I'll show you later. Certain errors are, or certain functions are removed from that and replaced by a constant. That's a very simple definition of counterfactual. And outcome of that, I still use it. I'm still call it a fundamental law, even though it can be derived from that. It's a law of conditional independence. It says that if you have in the model separation, a certain separation between variables, then you should expect to find conditional independence in the observed probability distribution that is implied by that model. Here I'm saying it here. Separation in the model implied independence in the distribution. Good. Let's see now how it works. Here I have a model. That's what I mean by a model. What is it? It's not a graph. The graph is derived from the model. The model is a collection of functions. Here the x is determined by a function w1, z3. Y is determined by three parents. We call them parents because in the graph they look like parents. But actually, it's a collection of functions. Okay, here is your model of the world, and here I am endeavoring to compute a counterfactual. What will be the value of y had the variable x been small x? Very simple. You cut off the arguments of the functions that currently determine the value x, and you replace them by a constant. You have a new model. I call it a mutilated model. Another collection of functions. The graph is only helped us describe it, but it is a collection of functions. And I have another collection of functions where I can calculate the value of y in that mutilated model. I call it y sub x. Done. I now have a simple way to calculate counterfactual. I call it embarrassingly simple. Here it is. Counterfactual are embarrassing simple. Once you believe in that, you are on your way to compute everything that you ever wished to compute from in the world, in the uh, sub sub field of causal reasoning. Of course, this is a subfield. It doesn't capture all of AI. There's no natural language here, and there's no vision here, but it's a collection, it's a subfield in the sense that it answers all conceivable causal questions. So intervention likely is simply computed by this formula. I use the term do to remind us that we have actions here. The result of intervention, do x equal to small x, is simply the counterfactual of y sub x had x been small x equal to y. So the probability of this equality. Good. Now we know how to compute interventions. We know how to compute counterfactuals. From what? Assuming that we have a model. Let's go forward and show an example. I think all of you know conditional, you know reading independencies or the backdoor criterion. So I'll go very fast. Reading independency is the second law of causal inference. Here's an example of a model, and here is what it means. It means that you have a collection of functions here. Each one of them depends on has in as argument what is seen here as parents and is subject to a certain noise u sub c, u sub s. These are economists call them error terms, and we want to now go to look at the independencies that could be read from that model, and every missing link in the model imply a certain independency. Here, for instance, if the use, here's the law. The law said that if the user are independent, the observed distribution of all four variables satisfy constraints that are number one, independent of the functions here, and independent on the nature of the probability distribution of those error terms. And that's a miracle. I call it a miracle. And it's readable from the graph. Every missing error implies a certain independencies. For instance, here is a missing error. It implies independencies among these four variables. Here is a missing arrow. It implies independency. And you know we have to deal with collider here. I wouldn't elaborate. The applications are enormous. Number one, it allows you to do model testing. What does it mean, model testing? To see if the data observed is compatible with a model assumed. You assume a certain model, and if you do not find this conditional independence implied or existing in the distribution of the observed variables, then you can rule out the model as incompatible. Also, you can do structural learning. You can say, let's look at all the subset of models that are compatible with the observed distributions. And perhaps we can get answers from a subset of those compatible models. And this is the idea behind um, causal discovery work. Then we can reduce intervention to question about adjustment of variables. And this is the calculus that I'm going to talk about. It is essentially reducing interventional question to symbolic calculus. If you take it seriously, you find out that derived from these two fundamental laws, there is a hierarchy of questions. The questions arrange themselves in a hierarchy which I call three-level um, tree, or a ladder of causation, which has the property that questions at level I can be answered only if you have either assumptions or information coming from level I or higher than I. For instance, at the lowest level, you have statistic association. If you see things, you can infer what you can believe in another variable. This is statistics. I liken it to the owl level of intelligence, where the owl zooms on its prey and can predict where the prey is going to be a moment later. And then you have intervention. The level of intervention enables you to answer questions about what if I do, or what would Y be if I do X? By do X, I mean if I make sure that variable X equal to a certain constant which I specify. Okay? So if I take an aspirin, will my headache be cured? What if we ban cigarettes? And the reason I put this example is because we never actually, in reality, banned cigarettes. And no society was able to do that. And we can still contemplate what will be the world like after if we ban cigarettes. We can talk about whether there will be black market in nicotine, whether there will be smuggling and so forth. We can talk about it because we have the ability to reason about what will happen if we intervene, even though we never in reality, in factuality, succeeded in executing the action under consideration here. And the last and most sophisticated level is that of counterfactual. It's about imagining, it's about doing retrospection. That's what I mean by understanding. It's the ability to answer question of why. What if I had done things differently? What if I hadn't taken, if I took another road, not the one taken? And for instance, we ask, going back, was it the aspirin that stopped my headache? So we know something about the future. Headache is gone. We know something about the outcome, sorry. And we ask about what could have been the cause of that. Would Kennedy be alive if Oswald had not killed him? And so on. Okay, I think you're all familiar with the three-level hierarchy from reading the Book of Why. So I'll go down and talk about the pillars of wisdom that comes out of this analysis. These are all tools that emerge from the two basic laws of counterfactual, fundamental laws of causal reasoning. The tool one is we are able to encode causal information in transparent and testable way. We have a mathematical tool, a mathematical object, which encodes the causal information, but it's encoded in such a way that I should say it not only transparent, but it is parsimonious. It's extremely parsimonious, and this is what makes it transparent. And plus, it is a testable way. I've shown you how things are tested. So we can predict, tool number two, predict the effect of action and policies. Okay. I'll demonstrate later how we can predict the effect of action. Actually, I've already shown you on the previous slide, but I can embed it in a more familiar example. Tool number three is to compute counterfactual. Again, we have seen it before, and which allows us to answer questions about attribution, about explanation. Some people call it susceptibility. And I'll go now to tool four because that is not part of that. It requires some additional work. We work on mediation. We can distinguish between direct and indirect effect, which is extremely important when we talk about questions such as fairness, for instance, the discrimination in the workforce or inequalities. So, tool number five, integrating data from diverse sources. In the machine learning circles, they call it transfer learning. You learn certain behavior in a laboratory and you want to transfer it into the field where conditions are a bit different. And you wonder to what degree you can generalize from what you learn in a laboratory to what you encounter in the real world. Okay? We call it fusion, or transportability, and we now have a complete theory uh, of that endeavor. So this is something that the causal inference has contributed to machine learning, because what happened in machine learning was a total failure. Transfer learning would never work. It was talked about as something that machine learning should acquire, but according to the expert, the result was an admission of failure. And I tell you, and we understand why. Because transfer learning depends on certain invariants. There are certain invariants that hold true between the laboratory and the field, and those invariants are captured by the causal relationship, not by a distribution. So if you only look at the distribution, out of distribution, in the distribution, okay, you cannot infer what remains invariant. If you have a causal model, you do, because the functional relationship in the model, those are the invariant. I'll go into tool 6, recovering from missing data. Mm, causal discovery, we mention it, but this is, I understand, is a growing field that I haven't spent much time in that, but I understand they have great results recently. And then I go to a tool 8, which is a personalized decision making. So I will go quickly over those 7 tools and go into the personal decision making, because that is what I believe to be the future developments in causal inference. Pillar number 1, I'm just repeating myself, but maybe elaborate and making certain points here. That the reason we can do this parsimonious encoding of causal information is because of a certain gift of God. The axioms of conditional independence and the axiom of graph separation happen to share a common core. And these are the axioms, the graphoid axioms that you might find in the book Causality. And this is really fortunate happening that deserve the name a miracle or gift of God. Yeah, I'm just repeating here about this operation here, but it's based on the discovery uh, that we have here share certain axioms which are shared by two objects which appears to be totally foreign to each other: probability theory and graphs. Theoretically, they are strangers, different kind of mathematical object. And it so happened that they share a set of axioms common to both of them. So graph separation and conditional independence. I'll go to pillar 2, control of confounding. The question is always determine if a desired causal relation can be estimated from the data and how. This is the question. And the solution that we have today is totally demystified and reduced to a game. We, we have tools like the back door adjustment, front door adjustment, and the do calculus, which generalize them and ask the question, can you predict the effect of a policy intervention whenever it's feasible? Not only when you have a certain pattern, but get an answer, is it or isn't it feasible? And completeness is another gift of God that tells you, if I tell you that it ain't, it cannot be predicted, then no one can do better. That is the nature of completeness. No one, no other framework can do better. I'm saying it because some people will tell you, why don't you do the Neiman Niemann-Rubin model? Or why don't you use some newly invented framework? Whenever I see a newly invented framework for causal reasoning, I'm suspicious. And I'm saying, can you do better than that? And the answer is mathematically no. No one can do better because if do calculus tell you it can be done, then no one can do with the same set of assumptions unless there are additional strong assumptions. Good. Pillar number three, the algorithmization of counterfactual. Okay. Give it a model and data, determine what Joe's salary would be had he had one more year of education. In another example, okay. Its social scientists or educational department is very interested in. A solution is the probability of every counterfactual can be computed or bounded using the surgery procedure that we saw earlier by mutilating the graph. And the corollary is that the causes of effect and attribution is now formalized. Here's an example that I usually take for attribution. I do it because in a minute I'm going to talk about assigning a responsibility, social responsibility to actors or event. So here's an example where a lawyer argues for his client, Mr. A, claiming, Your Honor, my client died because he used this drug. So I would like to the manufacturer of the drug to pay compensation for the family of the deceased. And the law is very clear about it. And if you look at the way that responsibility is assigned in the cases of that nature, um, the law must decide if it is more probable than not that Mr. A would be alive but for the drug. This is a language that lawyers are using, not me and not mathematicians, but it's taken from the lexicon that courts provide a decision or instruction. The court should decide if it's more probable than not. Here we have a probability, but what is should be more probable than not? That Mr. A will be alive but for the drug. But for is a very famous criterion for assigning a responsibility in the court of law. And if we try to write it down, we counterfactually, we have what we call probability of necessity. We do observe two events. Mr. A is dead and he took the drug. So we have two observations and condition on these two observations, condition on the outcome and the action. We want to find out whether the outcome, being alive, would be true had the drug not been taken. Again, we're using here a subscript. And the court requires you to determine if this probability is greater than 50% or not. Okay? We call it probability of necessity. And in some cases, we do find that it is indeed, we can bound it in such a way that we find that the probability of necessity is equal to 1, in which case the jury should declare the defendant guilty. So in all these cases where Pn can be bounded about 50%, the answer should be yes. Guilty, the guilty verdict is justified. Definitely, if the Pn happens to be 1, and this is a surprising situation where a certain combination of observational and experimental data gives you a bound which behooves you to believe that the probability is 1. Combined data sometimes tell you more than each study alone and brings up the probability of necessity to 1. Why do I bring that? That will be also the same situation that we'll see when we talk about personalized decision making. So, so it's a good introduction. Pillar 4 mediation analysis. Given data and model, unveil and quantify the mechanism that transmit changes from causes to its effect. And the result of this exercise is that graphical representation of counterfactual tells us when direct and indirect effects are estimable from data, and if so, how unnecessary or sufficient mediation is for the effect. Then, as I mentioned, it comes up in question of determining discrimination. For instance, here we have a gender variable. Here we have hiring. Here we have qualification. We ask, what is the direct effect of X and Y? Why? We ask it because the employer is responsible for this link, not about that link. This is a problem of society. It so happened that certain schools for girls do not prepare girls with a certain qualification for a certain job. But this is a problem of society, and this is what employers would be punishable if they allow discrimination, if they allow direct effect of gender on hiring. So the distinction between that path and that path is what makes an employer either guilty or innocent on hiring discrimination. Of course, one would say, but why don't you condition on M wrong? Because if we have confounders here, condition on M would create spurious path, and we are not going to block the indirect path. So we need to block the indirect path if we want to estimate the direct path. But how do you block the indirect path? By not conditioning on M, but fixing M, fixing the mediator to a certain value. And how do you fix things? Like computing the counterfactual, as if M was determined. Had M been, had qualification been a certain value. And indeed, the court articulate. Here is a legal definition of discrimination. Find the probability that the employer would have acted differently had the employee been of different sex or qualification had been the same. So we keep the qualification the same, and then we look at the remaining residual relationship between X and Y. So it is in the language of lawyers, except that they didn't, lawyers normally do not algorithmicized counterfactual, but what we have here is a nested counterfactual, which is captured by the idea of um, average direct effect. Direct effect. Here is the expression for direct effect, the natural effect, we call it, and it contains a nested counterfactual. But the fact that it is a nested doesn't scare us because we all agree that counterfactual are embarrassingly simple to compute. Good. We go to pillar 5 now, transfer learning. And that is the work done by Elias Barenbaum. And the task is to train, to find, to generalize um, uh, generalize what we learn in one domain to another. So here's the task. A machine trained in one environment find that environmental conditions change. When and how can it amortize past learning to the new environment. And solution is we do have today a complete formal solution obtained to the do calculus and using what we called selection diagram. Selection diagram are simple diagram where you uh, assign a variable to a potential source of the disparity. You have a disparity between two environments and you attribute the disparity to a certain cause. It's an unobserved variable, but you know its position in the graph. If you know its position in the graph, you know what other variables are affected by that directly, which are affected indirectly, and which are unaffected at all. And that allows you to here's an example of a problem. Um, Let me show you here an example. You have information coming here from several states, Texas, San Francisco, Arkansas, Wyoming, Toronto. Each one has a different condition. The data is obtained in a different manner. Here you have a server data, but here you have another server data, but the population is younger. Here you have a randomized trial here, but the samples is restricted to college students, and as we all know, college students are a different kind of population with their own idiosyncratic properties. So the question is, how do we put all these heterogeneous data sources together to come out with an answer to a query, find the causal effect in the target population in Arkansas, for instance, that has not been part of these experiments. And we can do it through selection diagram, and once you formalize it mathematically to those diagrams, you do have a calculus. It allows you to combine this together and see whether the query in the target population can be answered. Missing data, I wouldn't spend too much time on that because it's available now in a paper in the, I believe it's hmm, uh, in statistics. So it's available, and the problem is that you have under in many conditions you have missing data in the table. You simply have unavailable. Sensors tend to fade. Customers sometimes refrain from answering questions. They forget the situation, that they forget the answer to the query. So instead of value for a variable, you have the symbol M, missing data. And you have to answer questions that find, as an example of a question, is there a consistent estimator of the joint probability of XYZ as if no data was missing? Can you compute with this missing value the joint probability of XYZ as if no data was missing? And we have a complete answer for that. Sometimes yes, sometimes no. All depends on the reason for the missingness. So if you model the reason for the missingness, you do give an answer to questions like that, as if no data was missing. I'll go skip on that. Good, because I'm running out. I believe I'm running out of time. How much time do I still have? Can anyone give me an estimate?
5 minutes.
5 minutes. Okay, good enough to cover pillar number eight, introduction to personal decision making. Look at these two different counterfactual expressions. That one which we call P benefit, and that one we call ATE, which is average treatment effect. This is what we measure in a randomized control trial. What do we measure there? We measure the average of the outcome under treatment and the outcome under no treatment for a certain segment of population characterized by the properties of the population. This is the C character. Compare it to this one. This says, for instance, take the same character subpopulation, okay, but compute here the probability that a patient will recover had he been treated, and simultaneously, look at the end here, not recovered or die had he not been treated. So here we are talking about an individual you with certain characteristic, and we ask whether he or she will benefit, namely whether it will be, benefit means recover if treated, not recover, the same individual under the same condition, the same property, will not recover had he not been treated. So here we have something which is cannot be, no, usually cannot be estimated, because one of the problem of, some people call it the basic problem of causal inference, that you cannot observe the same person both being treated and untreated. You also get either one or the other. However, uh, we do have a calculus. The calculus can sometimes overcome the shortcomings of physical situations. Although we cannot compute or not observe a patient both treated and untreated, we can infer what that probability be by using the calculus. The example of why it matters, why the difference between P of benefit and ATE matters, just look at the, I'll give you, I'll try to convince you that it matters in decision making. Why? Consider an example, or consider the difference between two different models. One says there's no, imagine there is no effect in the experimental trial. So 8 is equal to 0. Those who are treated look the same as those who are not treated. Okay? Two different models can explain that. One says that there is no effect whatsoever on any individual. The other one says that uh, there is a balance here, that the drug cures 10% and kills 10%. So you don't see the difference in the randomized trial, but it has effect on individuals. Now, does it matter whether you have model 1 or model 2? Here's model 1, the drug has no effect whatsoever on any individual. The other one says that the drug saves 10% and kills another 10%. So these two balance. These two, see, benefit and harm, they are equal to each other, so you don't see it in either model, in the randomized trial, but it matters for the individual. But the question is, who really cares? For whom the difference makes? Should anyone care between the two different models? And the answer is yes. Number one, the patient cares. Okay? Model one is useless, but could be but safe. So if it has a certain beneficial effect, like if it really relieve pain, okay, model one will be preferred. And Model 2 may be scary or lifesaver, depending on the individual. It could be scary because if you have 10% of being harmed by the drug, you will refrain from taking it. You will think twice. So the patient care. Who else could care? A policymaker. A policymaker is not rated only by the number of people that are dead and the number of people that survive. Because imagine if we have autopsy and family discovers that that the loved one died because of the drug. He could have been alive today. Then the reputation of the hospital and perhaps the reputation of the entire healthcare system of the state would be damaged, not to speak about uh, lawsuits, but simply the reputation is something that a policymaker should care about. And the researcher should also care about because the differentiating allows you to look at and to search for markers for understanding the underlying mechanism that makes the drug differ, effective or non-effective for given individuals. So it matters. But in general, the probability of benefit and probability of harm cannot be point estimated from population data, but they can be bounded. And moreover, the bounds shrink when both experimental and observation data are combined, are available. And why? Because observational data gives you information about idiosyncratic property of the individual which are not revealed in either data source in itself. I should really rephrase what I said. Observational data gives you um, idiosyncratic properties of individual, which is not available in the experimental data. Okay, so let's go to the mathematics. Now, the mathematics allowed you to assign bounds on the P of benefit and from a combination of RCT, randomized control trial, and observational studies. Okay, and they further shrink if you have structural information. And this is the kind of work that Scott Muller has been doing in the past few years and published a few papers. And I see it as the future of healthcare systems because we can now get um, workable bounds on questions that couldn't be solved before. For instance, look at the problem of patients in need. You have influx of patients coming to a hospital, and you want to treat those that could be most could benefit most from the treatment. You don't want to treat people who are terminal anyhow. You don't want to treat people who would survive anyhow. Namely, that the drug is superfluous. Um, so you have to find and identify those individuals that could benefit.
We're about at the end of.
And yeah,
Sorry to interrupt. Just wanted to say that we're almost running out of time. Just wanted to let you know.
say it again. I couldn't hear.
We're almost running out of time, so I just wanted
Out
to.
of time. Okay. So, okay, I just impress you that we have this problem of identifying patients in need is generalizable to many other problems. It's all we call them situation specific decisions. What you really want to do in every case, in every decision making, you have a specific situation, a specific tool, a specific patients, a specific surgeons, and you want to find out for this particular situation whether a decision, one decision or another should hold. For instance, personalized medicine. For instance, identify customers worthy of recommendation or special offer. For instance, characterize voters which are swayable by a slogan or by certain campaign tactics. Okay? It's called the unit selection problem, and with a paper here by Lee Miller and myself. And I would just want to show you one. It leads to a decision making. Okay, you assign societal cost to for each selection for selecting individual of a certain characteristic, and you combine it by the theory of utility, and then you have to deal with bounds. I'm just sometimes the bounds are very clear. Here is a bound on benefit, bound on harm. Sorry, men and women. So you can distinguish between two and say, yes, the drug is beneficial to women, but it's harmful for men. And decision like that would lead you to a final conclusion that I'm about to summarize in a quote from Gary King from Harvard, saying that more has been learned about causal inference in the last few decades than the sum total of everything that has been learned about it in the all prior recorded history. It's a sweeping statement that I would only like to modify slightly with what we have learned from in these few decades. Medicine is on the brink of a major revolution, and we can now answer situation specific um, questions that scientists have always longed to ask but couldn't. I will now, this is my advertisement. The Book of Why is available to you, and came to the end of my talk. I didn't talk about computer ethics, but of course, if you cannot quantify harm, you cannot talk about ethics. Ethics means do no harm. This is the vow, Hippocratic oath that every physician takes, and it's based on the idea of do no harm. What is harm? Harm is defined here in terms of getting adverse, a bad outcome if you do one thing, and a better outcome if you do to the same individual if you do the opposite. And of course, people vary in their perception of what's good and bad for them, and that also must be taken into account when we talked about societal or ethics in society. And when we worry about the impact of AI on society, we cannot regulate, we cannot talk about uh, how I'm going back to the same term. We cannot talk about being ethical or being unethical without the ability of algorithmatizing the notion of harm. And this theory allows you to do that. Thank you very much, and I'm opening, would like to answer the questions if you have.
Hi, Professor Pro. Uh,
Yes.
Thanks for your great talk. So, in fact, I have two questions. Uh, After the large language model came out, more and more people started to talk about the AGI. So, how do you think of the causality will be the, you know, indispensable component of the AGI system? This is my first question. And my second question is that if you believe that, I think if you would like the AGI system can do the intervention task and the counterfactual tasks, I think the key is to you need to construct a choreograph. So, but I know, in fact, we are still struggling for constructing the good choreograph, even for the specific scenarios. So, how do you think of for the AGI system we can we can figure out the good choreograph? Thanks. I'm not sure.
It's a good question, but but the completeness result tells you that you cannot, if you're not ready to make the counterfactual assumptions which are embedded in the graph, okay, then you cannot answer the questions. There's no way. You must have. On the other hand, um, the the, ba- the what the calculus does for you is take assumptions which are defensible and convert them into answers to queries which are not predictable ahead of time. What do I mean by that? I mean that the kind of assumptions that you need to make when you are building causal graph are defensible. For instance, all you need uh, the format, the relationship that you must capture in the causal graph are relationship of the following nature. Does does variable y listen to variable x? I reduce it to something which each one of us can defend or understand. The question is, does variable y listen to variations in variable x? And this is a very primitive kind of assumption of a relationship, listening to, which I believe it's the most primitive that you can think of. And we have a lot of experience and a lot of knowledge, scientific knowledge, that allows us to answer them, that allows us to defend them. But I agree with you, it's a transformation between assumptions and conclusion, and without assumptions, you cannot go ahead. But the whole idea of the causal inference calculus is to make the assumptions meaningful to a scientist or to any person, for instance, crossing the street or turning the light switch on. We know that if you turn the light switch, the light will come on. These are basic and defensible kind of assumptions that are mm, uh, deduced from everyday experience or from everyday knowledge of science, from the elementary knowledge of science. So that is my defense. Yes, we need assumptions. Also, I would say that the work in causal discovery, okay, allows you to go and look at the data and come out with a set of compatible with the data, yeah. But compatible model, and sometimes you can get the answers, or you can narrow down the set, and sometimes you can get an answer which is true for all subset of compatible models. Okay. So these are, and my understanding is that in um, commercial application of causal inference, people take it seriously, and they are using causal discovery method to get the graph from the data. Go ahead.
Do you want to say more? Okay.
I should say something about LLM because I thought that most of the previous session had to do with the relationship between the large language model and causal inference. Okay. So the trick that the large language models are playing is that the training data is not data that comes from the environment, but data that comes from people, authors, that constructed the text upon which the LLM models are being trained. Okay? So the authors of those texts have knowledge, have causal knowledge, and this causal knowledge is embedded in the text. Okay, so the constraints that the ladder of causation imposes here do not imply do not apply to LLM models. But what they do missing is a model of the world, and they have different kind of problem. They do extrapolation on the basis of a data constructed from authors who know, who have causal model, who embedded their causal knowledge in the text. So today the um, the deficiency of large language models is being investigated by as a new animal. We do not understand their idiosyncratic behavior. So, I think causal modeling or causal inference should be applied in our attempt to understand the dynamic of LLM models.
Okay, so thank you. So first, thank you, Professor Perle. So it's a very interesting talk. So I also have two questions. My first question is concerned about what you have said, what you have mentioned, the word model. So what do you think are the necessary element for this word model?
I have presented here a world model. The structural causal model is a collection of functions, right? Each one of them tells you who listens to whom. This is a world model of an individual. And it's the first time in history, I would say, that we have a mathematical object that we can say this represents the belief system of an individual.
Okay.
We didn't have that kind of thing before, notice. A lot of economists and game theorists talk about a world model, but they didn't have a mathematical object to represent it. What is a world model? Or what is the belief system of an individual? It's not the probability distribution of that individual. No. A world model means a model that allows you to compute interventions and counterfactuals, to do explanation and predict the effect of actions. Okay, this is the world model, and we didn't have it. This is the first time we have a mathematical object which represents a person belief.
Okay, and for this word model, for the SCM, so do you think so from your point of view, the SCM is a face of reality or perception of the reality?
Yes, yes.
So which
No,
do you
no,
think,
no.
the face of reality or is a perception of
No,
reality?
no, we can be doubtful about the world model, but we know that behind the scene, behind the curtain, there is a totally complete world model. This is the assignment of function to relationship among variables. Collection of functions. This is a world model. Sometimes we are inflicted with ignorance and we do not have a complete, I mean, most of the time, we do not have the functions that relates one variable to its neighbors. We do not have that. But assuming that such a function exists, it gives you already direction in your research. And the purpose of the calculus is to infer as much as possible, having only a partial knowledge about those functions. All you know is their impact.
Thank you.
Any other questions? Yeah. Get the microphone all the way to the other side.
Thank you so much for your talk, Professor Pearl. May I ask you,
Thank you.
typically causal graphs are taken to be acyclic, and so I've been wondering in an application where I may have only observed data, how can or should I justify the assumption of acyclicity?
Uh, okay. The structural causal models work for cyclic and acyclic models as well. So, yeah, both acyclic and cyclic. What doesn't work is the miracle of deseparation. There's what I, being able to read independency on the basis of independence from the graph. The second fundamental law doesn't work, but the first one does work, namely the definition of counterfactual and the computation of counterfactual from the model. So you lose. You have to do additional work. Yet the basic fundamental law is still applicable. Plus, in my book, Causality, I show some cyclical models which are being solved using the same technique. But I agree, the miracle of deseparation doesn't work. And
Thank
you
you
have
so
to
much.
do additional work.
One more question.
Thank you. Thank you, Professor. Well, my question is about this world model. The real world is kind of very complex, chaos. So I think you present a beautifully kind of model, which does that also accommodate kind of misperception, misbelief, or this misinformation, or even mistakes? Is that the world model is going to model to accommodate all this misbelief, misinformation, and even
You mean you want to have a knowledge that you are mistaken about something? You
exactly.
want it to be part of your knowledge. Oh, ignorance is very simple to represent, right? Either you take a couple of graphs and say, I'm uncertain between the two. Or saying, I'm missing information about a certain error. I'm not sure if the error goes one way or another. So this kind of uncertainty can easily be modeled. Okay. Are you looking for more than that? What kind of
Well,
application would what kind of question can you answer if you have a knowledge about ignorance?
because you have this calculus in the center, I thought that's kind of a ground truth, right? You have the three input to generate one
Yeah.
out, and this one of the inputs could be kind of a misperception, right?
Yeah, you might not have sufficient data, in which case the calculus will tell you you haven't got enough information, you don't have enough assumptions here. Please pay attention. If you only can get this kind of experiment done, you will be able to answer it. This is what the calculus tells you. With this kind of assumptions and that kind of a data, you cannot answer the query. Done. And nobody can do better. But if you can, and we haven't done it, but it can be exercised in such a way that the calculus will tell you if you only have that kind of information taken from this experiment, okay, you will be able to answer the query that you ask. That is doable.
Thank you. Thank you very much.
One more
And that's
question.
indeed how we envision an automatic scientist to be built, to determine what next experiments ought to be done in order to resolve the ignorance, to resolve the misinformation that we have currently, and to be able, everything gears after a query in order to answer the question, what kind of experiment should I do next? This is doable within the calculus. Go ahead.
Thank you, Professor, for the great talk. I have a question concerning the pillar on missing data. Particularly, I'm wondering if you have some missing if in our application we have missing data, but we have also high-dimensional measurements with a very little or no causal prior about. Do you think there is potential to solve this problem? Can we leverage these high-dimensional measurements to retrieve missing values?
I am not sure that I can answer your question because what we have done in the exercise of missing data is show under what conditions you can answer the question despite missing data. Okay, namely, what kind of assumptions you have to have about the reason for missingness. You must have something that tells you why is the information missing. And once you put this missingness in the graph form, you can answer the question of whether you need more information or is it sufficient to answer your query despite the missing data. Can we get an answer to query as if the information, as if the data was not missing? So I'm not sure to answer your question because the first thing you have to do is to look at what we can do today, what the theory of missing data can tell you today. We have a certain condition. Some of them are complete, namely telling you that you cannot do better. Some of them are still not complete. And so it's a theory that tells you here are the conditions that need to be satisfied in your knowledge in order to be able to answer queries despite the missing data.
I see.
Look at what we have done and see if you can weaken the assumptions or if you can do better.
Yeah, thank you very much.
Questions? Okay, so let's thank Professor Pearl again.